Welcome back. The objectives of this video are to use back substitution to solve three-variable systems. We'll introduce Gaussian elimination to solve three-variable systems, and we'll take a look at inconsistent systems and systems with infinitely many solutions. So let's take a quick look at back substitution. We want to use back substitution in row echelon form here. So we've got our three systems of equations, and intuitively this seems pretty straightforward. We know that z is equal to 2, so we can work backwards or from z equals 2 and substitute in to solve for y, and then go ahead and solve for x. So if z is equal to 2, we know that y plus 4z, or 4 times 2, equals 7. We subtract 8 from both sides, and we get y equals -1. So now we know y, now we know z. We can substitute into our first equation and solve for x. So x minus 2y plus 3z, which that's a 2, is equal to 9. So we have x plus 2 plus 6 equals 9. We subtract 8 from both sides, and we get x equals 1. So our final answer here is the ordered triple in the order of x, y, and z. Put them in alphabetical order. So our answers for x, 1, y is -1, and z is 2. That looks like a z, but that's a 2. And that is our ordered triple, and that's our final answer. Objective 2 is to use Gaussian elimination to solve a three-variable system. So our elementary row operations for systems of equations, we can interchange two equations. We can essentially move the order around and that kind of thing. We can multiply one of the equations by a non-zero constant. Okay, we saw this in the elimination method when I multiplied by -56 and I multiplied by 1,000. Okay, that kind of thing. And we can add a multiple of one equation to another equation. Okay, this we usually do to force out a variable, or to force a variable to drop out. And it's also used to get a coefficient to be a particular value, usually 1. So to get a coefficient equal to 1. But it might be some other value as well. And we'll see that here in our sample. So the goal of Gaussian elimination is to use elementary row operations on a system in order to isolate one variable. You can then solve for the value of that variable and use back substitution to find the values of the remaining variables. That was weird. So let's take a look at using Gaussian elimination to solve a particular system. So we've got a system of equations here with three variables, so we have three distinct equations. So we're going to take a look at the solution here and how this process works. Because the leading coefficient of the first equation is 1, you can begin by saving the x at the upper left hand and eliminating the other x terms from the first column. So what we're saying here is our goal in this situation is to have something that looks like this. 1x, and then we'll have a y, and we'll have a z equals some value. But we want the next one, we want 0x to drop out. We just get y and z equals some value, and then finally we get z equals some value. So our goal is to get it to our system to look something like this, so then we can just do back substitution. So by adding the first and the second equation, the x drops out here. So as you can see here, if I add these two, that's what we did first. We just added these two. The x's dropped out. -2y plus 3y produces a +1y. and 3z plus z gives us a 4z, and 9 and negative 2 is 7. So by adding those two equations, we get that middle equation. So we're in pretty good shape here. The next thing we're going to do is we're going to add negative 2 times the first equation to the third equation. And why we're doing that is we're going to get this x to drop out. So if we multiply the top equation here by negative 2, okay, we get negative 2x plus 4y minus 6z equals negative 18. When we add that to the third equation, so negative 2x and negative 2x, our x's drop out. We end up with negative y minus z equals negative 1. So that produces our third equation, a new third equation here. So take that, we just bring that down. So you may see here, we've got y and negative y. So we can simply now add these two equations together. We can add equations, our new equation 2 and equation 3. When we add those together, we'll get a new system. I'm going to rewrite the top two equation, x minus 2y plus 3z equals 9. And we have y plus 4z equals 7. And when I add those two equations, I get 3z equals 6. So if I multiply that equation by 1/3, or divide by 3, I get z equals 2. Now I can do back substitution and solve my system of equations. You'll see this is, I think this is the same example we had in the first one. So if z equals 2, sure enough, I solve for y by using back substitution like I did in the earlier sample. So y plus 4 times 2 equals 7. So I get y equals negative 1. And then, same as I just did a few minutes ago, equals 9. And I get x equals 1. And I have my ordered triple of 1, negative 1, and 2. So we've solved that system. Objectives 3 and 4 is to go through other possible solutions. A system of linear equations is called consistent when it has at least one solution. We've seen that before. And a consistent system with exactly one solution is independent. If there's only one solution, it's an independent system. Okay? Independent, you're on your own, kind of makes sense. A consistent system with infinitely many solutions is dependent. That's that overlapping line thing. So that does make sense. Those two are dependent on each other. They end up with all sorts of solutions, or an infinite number of solutions. And a system of linear equations is inconsistent when there is no solution. So here's an example of an inconsistent system of equations. We're going to get something like no solution here, or something like 0 equals 7. We're going to get some sort of false statement. So I've got my three systems of equations, and they walk us through the process here. We're going to add negative 2 times the first equation to the second equation to produce a new second equation. Essentially what we're doing here is we're going to drop out the x here in the second equation. By doing so, we have negative 2x plus 6y minus 2z equals negative 2. And I add that to the second equation, which was 2x minus y minus 2z equals 2. So what I've done here is I've multiplied this one by negative 2. And I get a new equation of 5y minus 4z equals 0. Now I want to drop out x again. Okay, I want to get rid of this x here by adding negative 1 times the first equation to the third equation produces a new third equation. So now I'm going to multiply that equation by negative 1. So I get negative x plus 3y minus z equals negative 1. And I'm going to add it to the third equation. X plus 2y minus 3z equals negative 1. When I add those two together, I get my 5y minus 4z equals -2. So I get that new third equation. Now you may recognize something here, that we have two equations that are the same, but they end up in different values. So pretty big hint here that this is not going to work. Finally, they say add -1 times the second equation to the third equation, or what I might suggest is subtract equation 2 from 3, and we get a new equation, or we get 0 equals -2. If I just multiply all that by -1 or subtract it all, helps if I write it correctly. Right? If I subtract all that and work with those two, I get 0 equals -2. And you can see here we get something that doesn't make sense. What? So we end up with no solution. And finally, a system with infinitely many solutions. So we're going to get something like 7 equals 7 or 5 equals 5, and we're going to get infinitely many solutions here. Our system, it looks like we're in pretty good shape here. If we add the first equation to the third equation, we will get our x to drop out. Adding x and -x, y and 2y and -3z, we get a new third equation, just 3y minus z equals 0. Okay, so we're going to drop out x. That's why we did that. Then if we add -3 times the second equation, so we're taking that second equation and multiplying it by -3. So on the side here, -3y plus 3z still equals 0. And then we add it to the second equation, which is just 3y minus 3z equals 0. Everything drops out. We end up with 0 equals 0. And we get that new third equation. And then you can see here we have an infinite number of solutions. So there's our introduction to solving three-variable systems. And we'll get more practice with this when I see you in class.